Hi, my name is Fira Jalani, and in this video, I am demonstrating my novel research called Software-Defined Cyber Agility for Active Cyber Defense. I have developed this as part of my PhD dissertation. It is an agile security architecture that enables programmable and on-demand functionality, configurability, and manageability of security and resiliency countermeasures against novel attacks like distributed denial of service attacks at both application and network levels. These attacks could be an aggressive DDoS attack or a stealthy DDoS attack. It also defends against man-in-the-middle attacks where the attacker targets availability of data or resources. It offers both proactive and adaptive defense against these attacks. I have used technologies like virtual networks and software-defined networking to develop this architecture. And the output of my work is Active SDN controller, which I'll be demonstrating in this video. I have used OpenALite framework to develop this Active SDN controller. It offers many primitive cyber defense functions and high-level cyber defense functions that can be combined in different ways to develop different cyber defense policies. One of the research group that I'm working with is developing an auto-resiliency policy language, and they are actively using this Active SDN controller to develop different policies. Here is the list of some of the policies and the functions offered by the Active SDN controller. In this video, I'll talk about reactive DDoS mitigation policy and demonstrate the ability of Active SDN controller to implement and execute this policy. Active SDN controller intelligently selects the minimum vantage points in the network to collect traffic analytics and use these to efficiently detect flooded links in the network. Once the link flooding is detected, the next phase is the detection of malicious flows. In the aggressive DDoS attack, the attacker sends attack flows with very high rate. These flows could be connection-oriented TCP-based flows or connection-less UDP or ICMP-based flows. Active SDN controller identifies these flows and immediately blocks all the malicious source IP addresses at the network level. However, in the stealthy type of DDoS attack, the attacker uses thousands of bots and each bot sends low-rate benign-like traffic. This attack is not detectable at the network level. We use a simple intuition, and that is the stealthy DDoS attack requires thousands of bots, and most of them would be the newcomers to a service, means visiting for the first time. So if we cannot segregate malicious flows conclusively, then we can at least identify these newcomers. So if there exists a high ratio of newcomers in the traffic during the attack, then we can safely assume that most of them are suspicious at least. We do not immediately block them. Instead, we segregate these newcomers to low priority queues for further inspection. This action immediately restores the bandwidth for the benign user. Here is the snippet of the policy that I'm talking about. This is the topology that I use to demonstrate the DDoS mitigation demo. For the experimentation, I remove few of the links to make sure that I get the right level of sharing, which then triggers the packet loss. First, in this demo, host H1 and H2 starts off by sending benign traffic. Host H10 is the victim. During the aggressive DDoS attack, host H4 and H5 sends high volume traffic. I'm using Scapy to generate different types of attack traffic. During the stealthy phase of DDoS attack, I initiate many a host which then sends benign-like traffic to cause flooding. Uh, so let's go to the demo. First, I use a script to execute the Active SDN controller. It takes some time to initialize and load all the required dependencies. So we wait. Now let's run the script that is responsible to create the topology. It also creates multiple queues with different traffic rates per port in the network to offer quality of service support. In the network, I intentionally restricts the bandwidth of links from switch S1 to switch S9 and from switch S1 to switch S8 to cause congestion. And for the reference of the topology, I am showing the topology figure here, and you can see for the reference you can see the topology. So host H1 and H2 have started sending benign traffic to H10, which is basically ping messages. Now host H4 and H5 start sending aggressive traffic. Host H4 TCP based, H5 UDP based, and you can see that on the receiver end H10 is receiving attack traffic, and at the same time you would see that the controller immediately identifies H4 as malicious and blocks its traffic. However, as H5 is still sending the attack traffic, you can see the impact of H5 on the ping delay. So the controller basically fetches statistics from the network, and if the packet loss is observed, it triggers DDoS mitigation process. And this process then takes the corresponding action as it blocked the H4. So for this demonstration, I have kept the statistics collection window a little bit longer to control the automation of this demo process. So now again in the next window, H5 will be blocked, and you can immediately see the reviving RTT delays from H1 and H2. Now I start the second phase, the stealthy phase of the DDoS attack. In this phase, as I have mentioned before, that I basically initiates almost 25 hosts, and they all start sending ping messages, benign messages. So the idea is that if the attacker has too many bots, he can still launch a DDoS attack. And here is the example that by just using ping messages from these 24 hosts, you can see that the RTT has been increased for H1 and H2. And as you can see, although packet loss is observed, but the Open Daylight was not able to fetch the statistics for all the new hosts which are now sending traffic in the network. So that is why in this window nothing will be throttled. So we have to wait another window. Again, I have intentionally increased the size of the window so that I can control this demo, and you can basically observe, so you can have enough time to observe what is happening in the demo. So statistics are collected and newcomers are identified and throttled, and you immediately see its effect on RTT, that they are segregated and now they are competing with each other for the bandwidth. So sometimes even though we have isolated them, but there may be effect. In this demo, in this they have been completely isolated, but the controller will still see some packet losses. And if the controller still sees some packet loss, the last phase of the DDoS mitigation was to migrate or reroute the whitelisted. So we will see this impact here. So as you can see, controller observed some packet loss, so it rerouted H1 from to the troubled path to the new path. And basically because I have removed few of the links from the topology, so that is why you are seeing this effect. If you have any questions related to my work or any other questions, you can reach me at my email address fidahussain.gilani at gmail.com. Thank you.